what do we get if we were to integrate this?
So U would be x cubed, and dv would be x. And oh, you just want the answer, don't you?
Oh,
okay.
X cubed.
Yeah.
But that is correct. If I wanted the pieces here, this is what we'd be looking at, right? So you get x cubed
E to the x minus 3x squared dx
plus 6x
plus 6x dx
minus 6
dx.
Okay, so don't forget your constant. Now, when I was walking around, pretty much everybody used the table format, which is fine. Otherwise, how many times did you have to do integration by parts here?
So many.
4.
3.
3, right? Because the last time you'll get the minus 60 to the x after you integrate the last piece. So yeah, you'd have to do it 3 different times if you were going to do it by parts every single time. So with the table method, you take your u and just differentiate all the way down. So x cubed, 3x squared, 6x, 6, and then 0. And then make sure you alternate signs all the way down. And then take your dv and integrate it. And then you just go across the diagonals there. Okay. So we're good with that? Anything from yesterday's assignment then? Any of those problems you want to discuss or talk about? Going once. Going twice.
I had a question, but then I looked at back at my work and I was like, oh, I put this down wrong, I see it.
All right. Then, let's go through our notes. So today we're just going to stick with same idea, integration by parts. We're just going to expand upon a little bit what we talked about yesterday. So, we did our Bell problem. All I want to do is go through a couple examples, talk about some situations you might run into when integrating by parts.
Let's find an endless loop or am I crazy?
Okay, so when we look at this, we can tell by looking at our two functions that if we start to do the table format, right? So the table format, we select one to be u. So in this case, what would we select to maybe be u? Sine x. And we'd let dv then be e to the x dx, right? Now if we started our table, so we take u, sine x, and we want to start differentiating. Well, if I'm going to differentiate, what am I going to get? Cosine x, then negative sine x, and then negative cosine, and then and so on, right? So it's going to continue forever. So if we tried, maybe we want to switch these around. Maybe switch up our u and dv here. But if I do that, what's going to happen with my e to the x?
You're going to have a lot of e to the x's.
You're just going to get e to the x over and over and over again, right? So if we try to use the table version, we'd have to go forever. We'd never be able to stop because they just keep cycling through their derivatives and we integrate the same process. It's going to keep cycling through the same values over and over again. So when we look at a problem, if we have a function or a part of our integrand that actually will end if we're differentiating, then we can use that table format to simplify the process if it's one that we'd have to do integration by parts multiple times. But if we notice, like in this case, that we have two functions that would just keep completely cycle over and over and over again, we have to go through our integration by parts. Okay, so we're going to have to go through that process of integrating and see kind of where it leads us. So, first thing, like we had originally stated, we're going to let u be sine x, we're going to let dv be e to the x dx. So then when we take u and find its derivative, du would be cosine x dx. When I take dv and integrate it, we get v is equal to e to the x. Okay. So, what is my first integration by parts going to result in? What would my expression below here be?
Just the after the equal sign?
After the equal sign, yep.
Sin x e to the x minus cosine x e to the x? Or minus the integral of cosine x e to the x?
All right, so in this case, we have u times v, so sine x times e to the x. And then we have minus the integral of v du, so e to the x cosine x dx. So here's what we'd be looking at. Okay. Now, if you notice on my, I think on my answer key, at least for a couple of the problems, I was actually writing out the original problem all the way through, right? So this might be something that you want to kind of start getting in the habit of, and you'll see why here in a second. But here's what we're looking at. When we integrate by parts, the first iteration gives us e to the x sine x minus the integral of e to the x cosine x dx. Okay? Now, we know that at this point, we look at this integral, and we have to do integration by parts again. We have two functions being multiplied inside our integral. So we start the same process again. We need to define a u and a dv. And again, if you're doing it more than one time, sometimes it helps to give a little subscript on your u's and dv's to help denote that it's a different integration by parts step. So we're going to let u be cosine x, which means du would be negative sine x dx. We'll let dv be e to the x dx again, which means v would be e to the x again. Okay. So, once we apply our integration by parts again, our e to the x sine x is just going to come along, because we're not doing anything with it right now. So we're going to have e to the x sine x minus, what are we going to have?
E to the x cosine x minus the integral of negative sine x dx.
There we go. So e to the x cosine x minus the integral of e to the x times negative sine x. Okay? Now, when we do this, here's what it looks like. So this is if we were to write it out with everything in it right away. And again, make sure that if you're doing integration by parts a second time, that minus in front of the integral is going to have to distribute to everything inside that second integration by parts step. So make sure you put that second part in parentheses to make sure that negative sign gets distributed through. Okay, so, oops. So if we're looking at this step right now, okay, so things to kind of take note of. If I were to look here, I've got a negative integral of negative e to the x sine x. What can I do there? Yeah, I can make this a plus, right? So we're subtracting a negative. We can factor that negative 1 out. So we really have e to the sine, or e to the x sine x minus e to the x cosine x minus, so I'm going to write this out here so we can see it. So e to the x sine x minus e to the x cosine x. Now we change this to positive because of the two negatives we have inside, but we're subtracting everything inside, right? So even though it became a positive integral, now it's going to become a minus. So we have minus the integral of e to the x sine x dx.
So is this gonna go in the circle as well, or does this actually have an end?
Well, actually, yeah, if we were to continue this, so now if we looked at that integral and said, okay, well, now I've got the product of two functions again, I'm going to have to integrate by parts again. But what's going to keep happening as we go through this? It's just going to keep cycling over and over and over. So when you see those the products of two functions that you know are going to keep cycling through, since it's going to cycle through, what does that mean is going to happen at some point?
You're gonna end up back at the start.
You're going to end up back at what you started with somewhere, right? And for us, that happens right here. Look at the integral we're working with right here.
Oh, hey.
Okay? So we have the integral of e to the x sine x dx, which is what we're trying to solve or compute right now. Correct? So what we can do here, since these are like terms, they're both the same integral, we can combine them, right? I can take this integral of e to the x sine x dx and move it over and combine it with my integral of e to the x sine x dx over here. So if I had one over there, I'm going to need to add this over to the other side. I'm actually going to have two integrals, so 2 times the integral of e to the x sine x dx. And that's equal to e to the sine x, or e to the x sine x minus e to the x cosine x plus c.
Well, that's a thing.
But I don't want to know what 2 times the integral equals. I want to know what the integral equals. So what would I do next? Divide by 2. So my overall integral, and you can distribute it through if you wanted to. I think in my answer key for today's note or today's assignment, I'd do that. So you have 1/2 e to the x sine x minus 1/2 e to the x cosine x plus your integration constant c. So what you're looking for here, when you see your integrand has two functions that you know are going to keep cycling, you're going to start your integration by parts, and you're going to have to at least do 1 or 2, possibly 3 different iterations. And what you're looking for at the end of each one, you want to look and see, have I reached my original problem yet? So after the first iteration, we didn't get our original integral back, so we did it a second time. When we did it a second time, though, we found the exact same integral we started with. As soon as you do that, you have like terms that you can combine together. So you would add or subtract or whatever you need to do to get this integral over to the other side, and then take whatever coefficient you end up on the integral, divide it back over into the functions that no longer require integration. You want to see that? Okay, so on these types of problems where you notice you're going to have cyclical functions, the table format's not going to work because you just keep spinning your wheels over and over again. So this is where you have to go through the integration by parts, and every time you get a new integral, check to see if it matches your original. And as soon as it does, combine them, divide out whatever you have as a coefficient. That make sense? Okay. Let's take a look at this one. Now this one, if you want to, you can just kind of follow along. This is not one that's going to have any special new property. It's just some more practice, make sure we really understand where we're going with this integration by parts. So if I'm looking at this, square root of x ln x dx, what would I want my u to be? What would I want my dv to be?
The u should be ln x,
The u should be ln x. Why?
because going back to the complex.
Yeah, because integrating natural log of x is kind of an issue, right? So we want to make that our u so we can take its derivative, which is really easy, and then we'll integrate that square root of x. So if we let u be the natural log of x, then du is 1 over x. Or 1 over x dx. We let dv be square root of x dx, which means v, when we integrate, would be 2/3 x to the 3/2. So that's just our general integration rule. So when we apply our integration by parts formula, we take u times v, 2/3 x to the 3/2 times natural log of x, minus the integral of v times du. So 2/3 x to the 3/2 times 1 over x dx. So once we get to this part here, the first term, the 2/3 x to the 3/2 ln x, that's just going to stay like it is for good here. Our second term, now we're going to have to do a little work on. So we can simplify this a little bit to make this easier to integrate. So we can move the 2/3 out front. And if I take x to the 3/2 times 1 over x, that's just going to reduce down to x to the 1/2. And so now we can integrate x to the 1/2 dx. By getting another 2/3 x to the 3/2. But we already had a 2/3 out front, so that's going to become 4/9. X to the 3/2 and then plus c. Okay there? Okay. Application type of problem. Finding volume. Kind of like we discussed yesterday, finding the volume of a region. Same idea here. So suppose we want to find the volume of the region bounded by y equals 0, x equals e, and y equals natural log of x, rotated about the x-axis. So on the graph here, we have our natural log of x function here. And then we have our boundaries. So we're looking at taking this area here and rotating it about the x-axis. So, in this problem here, I chose to use shell method. Now you could use disk in this case, right? So if we use disk, we keep things in terms of x. So you could do that. Then your integral would go from 0 or from 1 to e would be your bounds, and then you'd have to solve from there. Otherwise, you can use the shell method by going from 0 to 1 on your integral. And natural log of x is pretty easy to solve in terms of y. Just raise each side to the e. So that's where this e to the y is coming in. So what we're looking at is slicing here and using things in terms of y. So if we're looking at the radius of our shells, the radius is going to be wherever we happen to be in y. And then the height of our shell would be the right function e, or right expression e minus the left e to the y. So that's where this e minus e to the y is coming in. And then we're going to evaluate from 0 to 1. So now here we have a definite integral that we have to integrate, and in this case, we're going to have to integrate by parts with it. So then our next step, we can separate out. So in this case, I'm going to separate it entirely into two separate integrals. So that way we can see where we need to integrate by parts and not. So if I distribute the y, we get e times y minus y e to the y. I can separate those into two separate integrals. So the integral from 0 to 1 of e times y dy. Now notice on the second integral, what have I left off?
Bounds.
The bounds. Okay? So we're leaving off the bounds for now because when we look at that integral, we're going to be integrating by parts. So when we integrate by parts, we're integrating indefinite integrals. We'll add in the bounds once we get back to where we want to be. Okay, so if you're doing this, you can take the bounds off and integrate. Make sure you put them back on at the end though. Okay? So, if we're doing this, my first term is just a straightforward integration. So I had e times y. If I integrate that, that's e over 2 times y squared. So there's nothing to do there as far as special property is concerned. If we look at the second part, okay, so I took the liberty of integrating by parts. Now this is one we could use the table if we wanted. So our u would be y, derivative would be 1, 0, and then the other one would be e to the y, so we just have e to the y over and over. Right? So we'd have minus y e to the y minus e to the y. And then from here, you can simplify this down, but then you'd evaluate from 0 to 1. So the only difference on this type of problem with the definite integral is once you get to your integration by parts, you're going to integrate by parts first, and then put those bounds back in and evaluate. You okay with that? All right. That's it. So here's your assignment. Get the examples kind of short today because, now this is not that much, in fact, I think it's about the same number of problems as you had yesterday overall. But this one will take a little bit longer because you do have about 2 or 3 of those problems where you're going to get those cyclical functions. So you're going to have to work them through a couple steps of the integration by parts. So they're going to take you a little bit of time to work through. Actually, while I'm thinking about this, you can go ahead and you can get rid of number 51. So number 51 you can get rid of. So I think number 25, they ask you to integrate x cubed sine x dx. And how would you do that? Use the table method, right? Well, on 51, the instructions say solve or integrate the given functions with the table method, and 51 happens to be x cubed times sine x dx. So they were expecting you to do 25, actually integrating by parts 3 straight times, and then they tell you to do it with the table method. Don't worry about doing 51. If you're already going to do the table method for 25, you've already done it, you're done. So go ahead and get rid of 51 on that list.
You can write it.
Can
Alex, can I take a picture of that? How would I do that?